Today's agenda, we will go through what is the basic linear regulator, and then followed by the LDO tips and tricks. It will covering the noise power supply rejection ratio, as we call the PSRR, and also the thermal performance, and lastly, so nothing we may be ignored in the real application, but it's very important. So we need to care about the transient performance during the dropout, near the dropout. So lastly, so we will also talk about the advanced LDO applications. So in this advanced application, we will discuss the parallel LDO using the ballast resistor. And then, so sometimes some application we need to regulate the current instead of voltage. So we can use the LDO to regulate our actual current. Yeah. So lastly, when one source it cannot supply the load very well, so there is some the application we can draw the current from the multiple input. So we will talk about the multiple input single output LDO. So at the top level, there are two types of power supply: the linear regulator and the switching converter. So for the switching converter, so it includes the switching elements and the low pass filter. So switching element will generate the square waveform. So we need to get a low pass filter and to control the output voltage. Compared to the switching converter, the switch working on the either fully on or off. But for the LDO, the internal switch is a passing element, and the switch is always on. So it's different. Yeah, that means, so for the LDO, it are often very simple, very cheaper, but it contains the very less noise than the switching converter. Yeah. In some of the very noise sensitive application, yeah, so LDO, we can a lot of LDO application. So of course, for the LDO, there is the drawbacks. When this equation for the efficiency is pretty simple, but we need to care about especially for the input voltage. If we choose the right input voltage, yeah, for example, it's very near to the output voltage, so we can also get the very high efficiency. Yeah. So the right is a plot for the efficiency. So during some heavy load, we can, from this curve, we can see the red curve represents the switching converter efficiency. So we can see there the higher efficiency compared to the LDO. But at light load, yeah, in most of the cases, we will need to care about this. So some maybe for some SOC, some MCU, yeah, sometimes it will working on the light load for a long time. Yeah, this is the spec for the LDO efficiency. Yeah, so LDO has a light load efficiency benefit, and so on the right corner here, so it shows a different output voltage. So the green is output voltage is 5 volts, and the red is 0.5. So that means as output voltage increase, so the input, if the input voltage is fixed, so that means the efficiency will be higher. Yeah. From this equation, it's easy to understand. So let's what is the structure for the LDO? So let's see, normally it's contained this block. Let's see, it will definitely need a reference voltage and also the error amplifier. For the error amplifier will adjust the difference between the output voltage and since the output voltage and the reference, and magnify the difference and also regulate the output voltage as we expect. So for the feedback resistor, most of those LDO are integrated this. But some LDO also you can adjust the feedback externally. So for the LDO, there is some key characteristics, including the dropout voltage, power dissipation, and because it is related to the thermal rise of the LDO, and also for the noise sensitive application, noise and including the internal and also the external. So the quiescent current and stability turn-on time. So what is the dropout voltage? So LDO require a minimal voltage to regulate the output voltage. Maybe in the classic LDO, it requires 1 volts. But for most of LDO designed by today in the market, maybe only need 40 or 50 millivolts. It's very low, and it also help to optimize your LDO supply efficiency. So for thermal, it's very easy to understand. So after the power loss on the LDO, so we can estimate the thermal rise according to the thermal resistance. We can talk a little bit later about the thermal resistance. In addition to the LDO, for the thermal resistance for the every other RC, we need to also care about this thermal resistance. For the noise, it includes the internal noise. The panic is dominated by the internal reference and the error amplifier. Another is the PSRR. So PSRR measures how much noise from the input coupled into the output voltage. So if the PSRR is very high, that is what we want, get this spec. And for the quiescent current, for some of the wearable equipment, we need the very lower quiescent current. So stability, most of the application for LDO is not so hard because it only need some the output capacitance were less, maybe less 10 microfarad. But some LDO also integrate the output capacitance, so you don't need to add anything externally. So it's very easy for if you choose this LDO like this. For turn-on time is a short time. It defines after the input supply applied to the LDO, the output voltage is rise to its regulated output voltage. So it's been like the startup time. So let's talk about the noise. So for noise, there are two methods to measure. One is the noise spectral density. The unit is microvolts per root hertz, and another is total output noise. The unit is microvolts. So for this, it's very easy. It's only integrated for the noise spectral density here. So if we want to compare the different LDO noise, so we need to make sure the the comparable frequency. If we want to compare a different LDO, we need to make sure the frequency range is the same, because previously we measured noise from the 10 Hertz to 100 kilohertz, but now mostly is 100 Hertz to 100 kilohertz. So what conditions do not affect internal noise? Let's talk about these three parameters. One is output current, input voltage, and output capacitance. So from this curve, as the different output current increase, but from this curve, it's nearly the same. But there is an exception. So for some very ultra low quiescent current, the load current will increase the noise. Yeah, this is the exception, but most LDO have not this influence. So for the input voltage, yeah, let's take a look at here. Input voltage from 1.5 to the 5 volts. Yeah, so the curve is pretty similar. So there is no the influence. Yeah, from input voltage, different input voltage. And for the output capacitance, as we can see here, so even we increase the output capacitance to 100 microfarad, so there from 10 Hz to 100 kilohertz, there no the big impact on the noise. Yeah, only a few changes on the very high frequency here. So we need to care about this. So if some noise in your application is very important, so but if you only change the output capacitance, it's need a lot. So it's better to check other noise source or the spec here. Yeah. So what conditions does affect internal noise? Let's see. As we mentioned, so for the internal noise, it including the reference noise and also the error amplifier noise. So we can see the first parameter. One is the feedback resistor. Yeah, because feedback resistor will influence the error amplifier gain. So because the gain will magnify the noise here and to the output. So let's set an example, very easy example for the output voltage is 1 volts. So the reference is 0.2. So the feedback resistor will divide 1 volts to 0.2 volts. Yeah, but for the error amplifier, so it will the gain will increase. So that's why some of the LDO the reference is the same as the output. So if the reference voltage is the same with the output voltage, so there is no influence on the internal noise. This curve will show us the feedback resistor, the different voltage, and with the external or internal feedback resistor, there's some the influence on the noise. Another parameter we need to check is the feed-forward capacitor. Yeah, so just like the switching converter, usually we add the feed-forward capacitor to improve the bandwidth. So here is also the LDO. It can be applied to the LDO side. Yeah. So if the LDO integrates the feedback resistor, we add the external capacitor here. So indeed, there is some the influence. Even with the feed-forward capacitor is only 100 nanofarad, it can improve a little bit. Yeah, but if the error amplifier input voltage reference is the same as the output, yeah, even we add the feed-forward capacitor, it doesn't matter for the noise. Another thing is if you choose the LDO with a pin, that is the NR, the noise reduction. So that means we can add a capacitor here on the VNR pin. So internally, there is also a resistor. So for the reference between the reference voltage and the error amplifier, so there is a RC filter. It form a low pass filter here. So that also can improve the noise. Yeah. So we can see this curve with the different noise reduction capacitor. We can also get a little bit the noise reduction here. Another spec is we need to care about the PSRR. Yeah, so if you test a switching converter or the LDO, so we very care about the input voltage and the output voltage. And another is the AC voltage for the output ripple. So PSRR is a spec for what is the input AC ripple coupled to the output here. So the equation is very simple. So we can see here. And there's a different frequency influence. So here it is a map. So from the low frequency range, yeah, from 10 Hertz to 200 Hertz. So the noise is from the reference and the resistor capacitor filter. And from the 200 Hertz to 100 kilohertz, yeah, for this, the internal error amplifier open loop gain is we need to care about. It will influence a lot. At very high efficiency, about 200 kilohertz, so the parasitic capacity will affect a lot. So, but for internal the FET, we can change. We cannot change. So we need to change a different LDO with less parasitic capacitance. And also the output capacitor is also important. So we need to choose a very low ESL capacitor here. And also if you choose a bigger value of the output capacitance, it will help improve the PSRR. So what condition does not affect PSRR? So on the left, the bar supply. So with the different bar supply, so the PSRR is nearly the same because the LDO bar supply only needed for the internally circuit function only. So if in case the bias above the minimal voltage required by the LDO, yeah, it can behave all the same function as the PSRR. Another is the output voltage. Yeah, so with the different output voltage, yeah, there are some the small impact. Yeah, with the different frequency, especially in the low frequency here. For the output capacity, we can also increase the output capacity to improve the PSRR, but the benefit is not so big. So very small impact only during the high frequency range. So the cost will be higher if you only increase the output capacitance. So what does also affect the PSRR? So as we know, so if we want to the LDO to regulate the output voltage at the some level we want, we need to the LDO or LDO internal fat or for the fat we need to it working on the saturation region. But if the passing fat enter the linear region, so we cannot regulate because the voltage between drain and the source is very lower, so we cannot manage the output voltage very well. So this is very important here. Yeah. So, but for the with the different weighing, it indeed influence the PSRR because near the dropout, so the PSR will performance will be degrade. So let's see the continue for the output current. So with the different current, it's also indeed influence the PSR as the output current increase here. Yeah, we can see this below curve, and also the red curve is very light load. So we can see from this curve, we can see the PSR will drop a lot. Yeah, with the different frequency range. So when you choose the LDO with the NRP, so let's see what is the capacitor noise influence here. So even if you only with a very little noise reduction capacitor here, we can see the improvement for the PSRR. Yeah, for this orange curve, even with the 100 nanofarad, we also get the PSR improve a lot. Yeah, during the whole frequency range. So let's also see the feed-forward capacitor. Yeah, just like the feed-forward capacitor will improve the noise, and it also can improve the PSR from this the right curve. The feed-forward with the feed-forward capacitor 10 microfarad. Yeah, it also improve. Yeah, so compared with the noise. The noise curve we care about the noise at a very low level is better, but for the PSR we want the PSR higher is better. So in addition to the LDO noise, for the next session is about the thermal. Yeah, so if we want to the different LDO thermal performance, there will need a very standard so to compare. So GTEC committee define a parameter to how to compare the different LDO. So GTEC committee define this is a foliar board, and for the external is a 2 ounce copper, and for the internally the power and the ground alternate. On the right corner, for the trace will be routed to the IC pin, but for other someone else, so we need to fill the ground. Yeah, this is a GTEC committee define this is the keyboard. That is also the specific dimension. Yeah, so if you check the LDO datasheet, normally you can get a spec for the junction to ambient thermal resistance. This spec is very important. So before we get the prototype, we can use this thermal resistance to estimate the LDO power loss. So we can estimate the thermal rise. So if you get the prototype and also bring up your converter, you can using the thermal gun to get a thermal image on the right corner. So if you have the chance to get this, you could also use another parameter to estimate your junction temperature. So if you check the datasheet, you can also get a very basic. This is also the thermal junction to the thermal resistance. Yeah, junction to ambient. So next page is about the another parameter. Yeah, so we can use this parameter to get the junction temperature, because the junction temperature is very important. If the temperature is over your SC limits, it will shut down. So let's go back. So for this thermal resistance, we can also add some of the strategy to improve it. Yeah, in real case, our board is also bigger than JTAG committee defined. So that means the thermal resistance will reduce a lot. Yeah, maybe we can see this comparison. Above is the JTAG defined board, and this is a real board. So you will see that the JTAG thermal resistance about around 688.5 degrees C per watts, but for the real board, it's only a half. Yeah, 34. Yeah. So how can we improve the thermal resistance? So we can maximize the number of the thermal vias. Yeah, especially the via around the SC side. Yeah, and also for the PCB copper around the SC, we need to maximize maybe for the bottom side and also internal side. Okay. So another spec we need to care about is the transient performance near the dropout. So if the input voltage is very different with the output voltage, so that we have the headroom. But when the input voltage is very near to the output voltage, here in this case, we need to care about the transient performance. So we can catch a waveform, yeah, when we do the load transient, yeah, maybe from the current from the low level to the high level, and also the current from the high level to the low level. We can check the input output voltage and compared to the input voltage. We need to make sure, and this worst case, we have the room, we have the headroom, we have the dropout voltage, yeah, bigger. So after we talk about the LDO specification, the noise PSRR, and how we can improve it, we can also discuss about the parallel LDO. You know, some when the current for the load is increased, if you check the LDO in the market, they cannot meet your application. So maybe we need to parallel the LDO. Yeah. So in this case, this is the LDO parallel application. So for the parallel LDO, there are more benefits, such as the increased load current, reduce noise, improve PSR, and improve the thermal spreading and the reduction in headroom requirement, and also require the volume. But you cannot just parallel LDO directly. So, you know, for every power supply, including the LDO, the SC also have the variation. So the output voltage is not very same as the accuracy. So, in this case, if the one LDO has a very high output voltage, so it will take more current from this path. So that means you will only draw the more current such as the LDO 1. So it will destroy the LDO. Yeah. So But we can also improve this only adding a very resistor here, ballast resistor. So how can we calculate the value of the ballast resistor? So this is a model for the multiple LDO parallelly. So this is a voltage source denotes for the DC operating voltage for the LDO, and this VE1 denotes the error voltage, yeah, including the load regulation and the line regulation, and the RB1 to N is denoted for the ballast resistor. So if we using the KVL and KCL, we can easily to get this resistor and the equation here, but only assuming parameter is we can assuming the same ballast resistor. So it can make our design very easily, a lot easy. So if we assuming this equation, so we can also get this equation. So this is the plot for this equation. So from this plot, we can also get if the ballast resistor increase for the error of the for each LDO path will drop. So it will better for the current sharing between the different LDO. But the drawback is load regulation is worse. So yeah, because the voltage between the ballast resistor will increase. So you will got the very less output voltage here. So it's a trade-off. Fortunately, we can also get a very optimized point here. We can use two methods for the ballast resistor. One is the PCB copper, and another is the resistor. So for the PCB copper, if we follow about the IPC 2221, so we can easily get here. So compared to the maybe for the discrete resistor, it's the package will be bigger. Yeah, but you don't need to add more of the cost, even for only for a very discrete resistor here. So, but another drawback for the PCB is PCB trace is about the variation with the different the thermal. So as the temperature increase, the resistance will be increased. So this is drawback. Another option is a discrete resistor. Yeah, so we can use it as our application very usually, but we need to add it. But also for the derating for the resistor, we need to care about. Yeah, as the temperature increase, the power dissipation is also derating. So if you application is sensitive for the load voltage here, so sometimes we need to, in addition to care about this the LDO, also the ballast resistor, we need to care about the root on the PCB. So because the root also have the resistance, even from positive to the positive line and also back line. So we need to care about the PCB root resistance. But if the only for the ballast resistor below 50 milliohm, it can be meaningful. Yeah, such as if your ballast resistor is calculated by the 20 milliohm, but on the PCB board, the PCB resistance is around 5 millivolts, you can get a ballast resistor 15 millivolts. Yeah. Another TI also developed a tool you can easily download from the TL.com. It can this tool is very straightforward. Firstly, choose a different LDO, and after you choose, you can also go to the LDO parameter, and then you enter your requirement. Yeah, spec here, temperature, maximum junction. Yeah. So after that, the tool will generate the ballast resistor recommendation here. So you can choose the ballast resistor close to the recommendation. So the step 5 is using the how many the LDO. This is a comparison for the parallel LDO side. This is the efficiency comparison between the analysis and the measurement. Yeah, so it match the same. So another is thermal. We need to care about, because we care about the current sharing between the different LDO. So you can see that for the different LDO, the thermal rise is pretty similar. So that means that we also achieve the good current sharing. Also, this is the output, the efficiency versus the load voltage. Yeah. So also we compare the one LDO and also the parallel, three parallel LDO, the noise. We can see here through paralleling the LDO, we can also achieve the noise reduction. Yeah, during the frequency winds from the low frequency to high frequency. But for the PSRR, it's no very great impact on the PSRR, even using the parallel LDO. But for the transient, it can improve a lot from this plot you need to care about here. Yeah. So there are some applications using the constant current, so such as the LED. Yeah. So in this case, if you want to your LDO to regulate the output current, so you need to choose the LDO with internally constant current. So for the output, for the constant output voltage, you can easily to only add a resistor here, but for the constant current, so you need to only add a noise reduction capacitor, and also another, in addition to the ballast resistor, you need to add another resistor to define your load current here. It's also pretty easy, just like the parallel LDO. Yeah. Another thing is so when the input source cannot provide enough current to your load, so fortunately you can get a different voltage source. So and this here you can also see here with a different source. Yeah, maybe one source only powering 5 volts and the other 2 volts. It can also combine to provide the full power for your load and meet your requirement. So it's also been like the parallel LDO. Yeah, the only difference you cannot assuming your ballast resist same. Yeah, because the input voltage is different. So this is the flow chart. So it's also been the same with the parallel the LDO, the same input voltage LDO. So from this flow chart, it's also very straightforward. Yeah, you can use this equation to get the ballast resistor, and it also denotes some of the worst case. Yeah, you can help. It will help your design, yeah, even for a longer time. Yeah. So this is performance for the parallel single input, single output, and versus the multiple input, single output. For the noise, we haven't seen any a lot of impact during the 10 Hz to 10 megahertz. But for the thermal side, yeah, here we need to care about. Yeah, so on the right is the input source is the same. And for the load current is up to nearly 10 ampere. And for each LDO, we have the 1.55 volts. And for this, so one source is 1.72, and the other is 1.25, and the third one is 1.09 volts. So you can see with the different input supply, the current is different. But from the thermal image, even the different input supply, but we also achieve the very good thermal performance. Another thing about the transient performance from here for the multiple input, single output, yeah, get the worse compared to the single input and single output here. So this is summary. Today we talk about the LDO basic and also the important spec for the LDO, noise, PSRR, and how to improve it. And then we talk about some advanced application, including the parallel LDO and the constant current LDO, and also the multiple input and single output LDO application. Yeah, so that's all. Thank you.